Hi, this is a revision video on shifting equilibrium, and this assumes that you have covered reversible reactions and you are able to recognize the symbol, which is just above here, where you have a half arrow forward and a half arrow backwards, instead of a single arrow for chemical reactions to show that a reaction is reversible. I hope that you've already covered that a reversible reaction is endothermic in one direction and exothermic in the other. If you have not done so already, then all you need to do is just scan the QR code, which I'm pointing to over there. You will actually see a demonstration that I have done that shows this for the effect of heat on hydrated copper 2 sulfate. The other compound that you also, I hope, have seen in class is hydrated copper 2 chloride, which you form when you add water to anhydrous cobalt 2 chloride. So I've got my mouse over here just to show you what I mean. The cobalt 2 chloride paper comes as this. It's a very, very pale pink. When you dry it and warm it just above 40 to 50 degrees centigrade, it turns into this really gorgeous deep blue color. And you can then test for the presence of water by adding a drop of liquid that you suspect water to be in, and the water will trigger off the color change, so it will turn from blue to pink. So this is primarily aimed towards my students who are taking Cambridge IGCSE chemistry, but this will actually help if you are taking any UK exam board GCSE, and because this is actually within the higher papers for those boards as well. And this is valid for 2023 onwards. So in today's session, what we'll be able to do is we'll be able to cover the following. You'll be able to state that a reversible reaction in the closed system is at equilibrium when the rate of the forward reaction is equal to the rate of the reverse reaction, and concentrations of reactants and products are no longer changing within that dynamic equilibrium within the closed system. And the second point that I'd like to elaborate on is hopefully going to get you to a point where you can predict and explain for a reversible reaction how the position of equilibrium is affected by changing temperature, changing pressure, changing concentration, and using a catalyst, using information that they provide. Primarily, the information that they provide will be in the form of maybe a chemical equation where you can actually see differences in gas volumes on the reactants and product sides, from left to right. But also they should be able to provide you with some information as to which direction is exothermic and which direction is endothermic. So they could give you a value, and they could say the forward reaction, for example, is exothermic, or they may say the forward reaction is endothermic. So you'll have to figure that out using the information that they provide. We're going to start off by being like just going through that important point. Whenever you see in a syllabus that the exam board asking you to state something, it's really, really important that you get yourself a revision flashcard and you just memorize it word for word. So if they ask you what is a reversible reaction, you can say in a closed system, a reversible reaction is a reaction that you have a forward reaction as well as a reverse reaction. So your reactants can turn to products, and the products can return back to the reactants. If they ask you about dynamic equilibrium in a reversible reaction, so you can actually say that, well, it's within a closed system. You need a closed system, so you can't have anything escaping. And when a reversible reaction is in a state of dynamic equilibrium, what we mean by that is the rate of the forward reaction is equal to the rate of the reverse reaction. So you don't really have over time many changes in the concentrations of the reactants and the concentrations of the products. Just a quick one about what rate means, because we like to use the word rate as chemists. The rate of a reaction is a measure of how quickly a reactant is used up or a product is formed. So I've got a little example for you. Have a look at this. This is a closed system, so you can see where the dots are. None of these little beastie yellow circles or blue squares can escape, and we've actually got a dynamic equilibrium happening. So what's actually happening is that you can spot that there are around about 5 blue squares that are changing to yellow circles at the same time as yellow circles going to blue squares. So this is just representing chemicals. It's irrespective of what the actual particular reaction will be telling you. Just understand that on the left hand side you've got yellows going to blues, and on the right hand side you've got blues going to yellows. If you watch very carefully, you'll actually see that 5 yellows go to blue and 5 blue goes to yellow. So there's no overall change. You're not starting to build up yellows throughout, or you're not suddenly finding that everything turns into a blue square. So it's very important for you to also notice, this is something I've purposely put into this diagram, that reversible reaction being at dynamic equilibrium does not mean to say that the concentrations of the reactants and the products are exactly the same. So you look at this diagram and you count at any moment how many blue squares there are, if you can. There are 1, 2, 3, 4, 5, 6, 7, 8, I believe. If you just 1, 2, 3, let's count with me. 1, 2, 3, 4, 5, 6, 7, 8. If you can just slip through there, you can actually see that there's 8 blue squares at the same time. But there are 7 yellow circles maximum at the same time as well. There's 4 there, and then it goes to 5, 6, 7. So the concentrations of the reactants and the products when you have a dynamic equilibrium may not necessarily be the same. When the dynamic equilibrium is established, you actually have the rate of the forward reaction being equal to the rate of the reverse reaction. So the number changing from one side to the other is the same number over time as changing back to the original chemical. So I've got a video, and I would strongly recommend that at this stage you just pause this video and you do your QR code with your device, and you scan the video that I have actually already loaded up onto YouTube, where you actually have this experiment. I'm going to, from this point onwards, assume that you have watched that video. So go away, have a cup of tea, think about it, and then come back over here. Right, so you've watched the video, and this is the still from around about 3.5 minutes in, and what I've done is I've just basically frozen the screen. So on the top left-hand side, you can actually see the pink cobalt species that I made, and you can also see the blue cobalt species on the right-hand side. Now, the blue was actually made in the presence of lots and lots of chloride ions, so I used concentrated hydrochloric acid to force this cobalt species to become blue. And in the second sample, I actually forced it to turn pink because I added lots of water. So basically, what's happening is the cobalt 2 plus ions are surrounded by either water or chloride. If there's more chloride present, you actually find that you form the blue species. If there's more water present, you actually find that you form the pink species. So it's a bit slightly linked to what we saw earlier when we had the cobalt 2 chloride paper. So there's lots of water, it turns pink, but when you can actually find that you replace the water with chloride ions, and when that happens, it just turns blue. So it's like as if none of the water molecules can bind with the cobalt. So you don't really need to know too much about the intricate nature of this chemical reaction. And the reason why I chose this reaction to illustrate what I'm about to show you in terms of shift of equilibrium is that it turns 2 very vivid colors depending on what kind of situation you are presenting to the cobalt species. So if you have lots of chloride ions, you can actually see this simplified version of the word equation. If you have lots of chloride ions, then you actually find that the pink turns to blue. If you have lots of water molecules in the presence of those blue, it turns back to the pink. Okay, so what I also wanted to illustrate in the video was that we could actually change color just by warming and cooling. So if we actually start off with a mixture of the pink and the blue, you actually find that you get violet. And it's really interesting to study the violet stage and warm and cool the violet solution. because you can then try and figure out what effect raising temperature will be on the equilibrium, because raising temperature actually does have an effect on a dynamic equilibrium. The reason why is because in one direction you've got an exothermic step happening, and in the other direction, the opposite direction, you've got an endothermic step happening. So for this particular reaction, when we warm it, we find that the pink goes to blue. And this kind of gives you a hint. If you are warming it, that means that you are supplying energy into the chemicals. Now, that's actually going to favor any endothermic reaction, as endothermic reactions actually take in energy from their surroundings. So the forwards reaction is actually endothermic. The reverse reaction is exothermic, and it's not helped by a rise in temperature. So more on that in a little while. But we actually find that when we cool the violet solution down, we get the pink species. You could also even think of it as being the reverse reaction is exothermic, and the energy that is transferred to the surroundings needs to go somewhere. So cooling it actually encourages that process, and that's another way of thinking about it. What's quite interesting is that you can warm and cool it, and it can go from blue to violet to pink to violet to blue. You just keep going as many times as you want. You don't have to add any chemical in order to change the color for this particular reaction. This makes it very interesting to watch. So there you have it. Endothermic, so more favored by warmth going in the forward direction. Exothermic, so less favored by warmth going in the reverse direction. So that's a link to the video. Please make sure that you watch that video, and you can pause that video as and when you need to. The equilibrium from that video can be represented by this equation. So let's add chloride ions, as we did in the video, to the closed system. So if it was violet and we added chloride ions, we would find that the forward reaction increases. There's more chloride ions to combine with the pink species. So that helps the forward reaction. It doesn't help the reverse reaction. So you get more forward reactions happening in a unit at a time. That means that your forward reaction rate increases. It becomes more blue and less pink. And what then happens is you build up the cobalt species on the right-hand side. So more cobalt species can actually then um, uh, bind with water molecules to form the pink. So you basically kind of re-establish the equilibrium. But the equilibrium actually shifts over to the right-hand side. So you kind of shift the equilibrium. You disturb it by raising the chloride ion concentration. More forward reactions take place, but then as the forward reactions take place, you lose your pink cobalt species, so the forward reaction rate starts to drop. The blue cobalt species is obviously picked up because you've made it, and that starts to drop because the reverse reaction is starting to increase now. And then what happens is your reaction rates start to equilibrate again. They become equal again. So they become equal again, but on the blue side. Okay. So the forward reaction rate drops, the reverse reaction rate rises, it stays blue, and we actually can say that the dynamic equilibrium is re-established. But it's re-established on the right-hand side because it's blue. If we add water molecules to the closed system, the reverse reaction rate increases because the blue combines with the water molecules. You have less blue present and more pink because the reverse reaction rate is increasing. We can say that the equilibrium shifts to the left. It shifts to the left until the reverse reaction rate starts to drop because you're using up all of your blue cobalt species. As you're building up your pink cobalt species on the left-hand side, the forward reaction rate starts to rise. So they start to equal out again. So it stays pink, but the dynamic equilibrium is re-established. So changing the conditions can actually change the yield. When this reversible reaction is in dynamic equilibrium, you've got to remember that the concentration of the pink cobalt species and the blue cobalt species did not change. The rate of reaction forwards is the same as the rate of the reverse reaction when you have dynamic equilibrium set up. Adding chloride ions means that you have more chloride ions now present in the closed system, more combine with the cobalt species, that's pink. More forward reactions then take place, and we see the solution turn blue as the pink species is used up and is not replaced until the forward rate drops to equal the rising reverse rate. And we can say that the equilibrium shifts to the right. If you add water molecules, the water molecules that are present can now combine with the blue species, increasing the reverse reaction rate. The solution can turn pink as the blue species is used up and is not replaced until the reverse rate drops to equal the rising forward rate. So in that situation, you need to be able to write that the shift is to the left. Now, exactly the same justification can be used for removing chloride ions. So if you remove chloride ions, you have a shift to the left because the solution is, if you have, you have a shift to the left because the reverse reaction rate is higher than the forwards reaction rate. Less forward reactions take place, the solution turns pink as the blue species is used up and is not replaced until the reverse rate drops to equal the rising forward rate. And a similar justification can be made for removing water molecules. If you remove water molecules, there's less that can combine with the blue, so then the pink is dominant because there are more forward reactions taking place than reverse reactions, and the solution turns blue as the pink species is used up and is not replaced until the forward reaction rate drops to equal the rising reverse rate. So we can then say that the equilibrium shifts to the right. If we raise the temperature, the forward reaction is endothermic, and that needs to take in energy from the surroundings in order to happen. A higher temperature, therefore, helps raise the rate of forward reactions. More forward reactions take place, and we see the solution turn blue as the pink species is used up and is not replaced until the reverse rate rises to equal the falling forward rate. We say that the equilibrium shifts to the right, and if we drop the temperature, exactly the opposite happens. The forward reaction is endothermic and needs to take in energy from the surroundings in order to happen. The lower temperature hinders and lowers the rate of forward reactions. You have less forward reactions, but you have a higher number of reverse reactions taking place. So the blue turns to pink because the blue species is used up, is not replaced until the reverse rate drops to equal the rising forward rate. So the equilibrium shifts to the left. Now, there's a lot of ideas here, so this idea will actually help you. When a reversible reaction is in equilibrium and you make a change, the system acts to oppose the change and restore equilibrium. A new equilibrium mixture forms. The reversible reaction always reaches equilibrium in a closed system, but by changing the conditions, you can shift the equilibrium to the right or to the left so that the mixture contains more product. Finally, I've just left you with a quick summary of predicting the effect of changes in conditions on equilibrium. And what I will do in my next video is I will talk a little bit more about the catalyst and about changes in pressure. But I'll come back to this this slide. But what we also need to appreciate and understand is that if you raise temperature, not only does it help the forward reaction, but it actually helps the reverse reaction as well, because ultimately chemical reactions require bonds to be broken, and that's usually in the first step, and that is something that requires energy to be transferred into the chemical system. But because some changes are endothermic, those ones will be favored a little more with a rise in temperature than exothermic changes. So I'll leave this on I'll leave you with this slide, because when you are going through your equilibrium past paper questions, I strongly recommend that you have this slide in front of you so that you'll be able to match all the possibilities. So all you need to do is just find the particular point in the grid. If you've got, for example, a temperature rise question, ask yourself this: is the forward reaction exothermic? If so, that means that the backward reaction is favored and the equilibrium shifts to the left, less products, more reactants. By using this grid, you should be able to handle any question, even multiple choice questions, that they can ask you in your GCSE for any particular change in conditions on equilibrium when they're asking you to predict the effects. I hope you watch my next video. My next video will be on the application of these principles in the Haber process and generating ammonia. And the following video after that will be talking about the contact process and how sulfuric acid is manufactured. Good luck in your exam. Take care. It'll be lovely to have some comments and your feedback. Please like and subscribe. I look forward to hearing that you did really, really well in your exam. Take care for now. Bye.